The universe has always fascinated humanity, a vast and enigmatic expanse stretching beyond the limits of our imagination, filled with celestial wonders and terrifying mysteries that defy our understanding, from the invisible forces shaping galaxies to the eerie silence of the cosmos that raises the ultimate questionnaire: we truly alone? Scientists have long sought to uncover the secrets lurking in the dark void, yet the more we explore, the more perplexing the universe becomes, revealing anomalies that challenge the very fabric of physics, such as dark matter, a substance that exerts immense gravitational influence despite being completely undetectable by conventional means, composing nearly 27% of the cosmos while remaining invisible, a ghostly presence that only manifests through the movement of stars and galaxies, warping space-time in ways that leave physicists grasping for explanations, suggesting the existence of particles beyond the standard model. Yet every experiment searching for direct evidence has frustratingly turned up empty-handed, fueling the possibility that our understanding of fundamental physics might be incomplete. A thought even more disturbing when considering the role of dark energy, an unseen force responsible for the accelerating expansion of the universe, accounting for 68% of everything yet defying all known principles of matter and energy. A silent yet overwhelming power that appears to push galaxies apart with increasing speed, raising questions about the ultimate fate of existence, whether the universe will expand into a cold, empty void where stars burn out one by one, or if unknown physics might eventually reverse the process in a cataclysmic collapse. All while black holes lurk in the depths of space, cosmic behemoths with gravitational pulls so immense that not even light can escape, their event horizons marking a point of no return beyond which reality itself ceases to function in any comprehensible way, potentially containing singularities where the laws of physics break down, their very existence challenging our understanding of space and time. And, while we have captured images of these enigmatic giants and detected gravitational waves produced by their violent mergers, we still lack fundamental knowledge about what lies beyond the veil, whether they serve as portals to other regions of the cosmos or even other universes entirely, a notion that ties into the greatest question of are we alone? The Fermi paradox highlights the unsettling contradiction between the high probability of intelligent extraterrestrial life and the deafening silence of space. Given the sheer number of exoplanets within habitable zones around distant stars, it seems statistically improbable that life exists only on Earth. Yet, despite decades of searching, we have found no definitive signs of alien civilizations, leaving scientists to wonder whether intelligent life inevitably destroys itself before reaching interstellar capability, whether advanced species choose to remain hidden, or if there are fundamental barriers to communication we have yet to comprehend. Further complicating matters is the possibility that our perception of time and space itself is flawed. As quantum mechanics suggests, reality at its most fundamental level is dictated by uncertainty, while general relativity describes space-time as a malleable continuum. Yet these two pillars of modern physics remain irreconcilable, pointing toward the necessity of a unified theory of everything that could unlock the deepest secrets of existence, an endeavor that continues to push the boundaries of human knowledge through experiments with particle accelerators, gravitational wave observatories, and space telescopes designed to peer further into the cosmic past than ever before. Yet with every breakthrough, new questions arise, each mystery peeling back another layer of the unknown, proving that the universe is not merely a vast expanse of stars and void, but a living enigma that taunts us with its secrets, daring us to uncover the hidden truths lurking in the darkness. Humanity's understanding of the universe has evolved dramatically over millennia, shaped by both scientific discoveries and philosophical speculation. From ancient civilizations gazing at the night sky to modern physicists unraveling the mysteries of dark matter and quantum mechanics, the journey of cosmic exploration has been one of relentless curiosity, groundbreaking revelations, and paradigm shifts that have redefined our place in the cosmos. The earliest civilizations, including the Babylonians, Egyptians, and Greeks, sought to make sense of the celestial sphere, using the movement of the stars and planets to create calendars, predict seasonal changes, and develop rudimentary cosmological models. The geocentric model, championed by Aristotle and later refined by Ptolemy, dominated human thought for centuries, placing Earth at the center of the universe with celestial bodies orbiting in perfect circles. This perspective, deeply intertwined with religious and philosophical beliefs, remained largely unchallenged until the Renaissance, when figures like Copernicus, Galileo, and Kepler began to shift the foundations of astronomy. Copernicus's heliocentric model, published in De Revolutionibus Orbium Coelestium in 1543, proposed that the Sunday, not Earth, was the center of the universe, challenging long-standing dogma and setting the stage for the scientific revolution. Galileo's use of the telescope in the early 1600s provided empirical evidence for this model, as he observed moons orbiting Jupiter, the phases of Venus, and the rugged surface of the moon, contradicting the Aristotelian notion of perfect heavenly spheres. Kepler's laws of planetary motion, formulated through meticulous mathematical analysis of Tycho Brahe's observations, further refined our understanding, revealing that planets move in elliptical orbits rather than perfect circles, a realization that paved the way for Newton's law of universal gravitation. The 17th and 18th centuries saw an explosion of scientific progress, with Newton's Principia Mathematica establishing the fundamental principles of motion and gravity that governed celestial mechanics. His mathematical framework allowed astronomers to predict planetary motions with remarkable accuracy, reinforcing the heliocentric model and demonstrating that the same physical laws that governed objects on Earth applied to the heavens. This period also witnessed the first real attempts to measure the vastness of space, as astronomers like James Bradley discovered stellar aberration, providing indirect proof of Earth's movement around the Sunday. The 19th century introduced spectroscopy, which revolutionized our understanding of the composition of stars and the universe itself. By analyzing the light emitted by celestial objects, scientists such as Joseph von Fraunhofer and Gustav Kirchhoff identified distinct spectral lines, revealing that stars were composed of the same elements found on Earth, a groundbreaking discovery that hinted at the fundamental unity of the cosmos. This era also saw the rise of nebular hypotheses, with astronomers speculating that the Milky Way was not the entirety of the universe, but rather a vast collection of stars among potentially many others. The 20th century ushered in a new age of cosmology, with Einstein's general theory of relativity in 1915, revolutionizing our understanding of gravity, space, and time. No longer seen as a static backdrop, space-time was now understood as a dynamic entity that could bend and warp in response to massive objects, leading to predictions such as gravitational lensing and the expansion of the universe. In the 1920s, Edwin Hubble's observations of distant galaxies provided definitive proof that the universe was far larger than previously imagined. By analyzing the redshift of galaxies, he demonstrated that they were moving away from us, leading to the formulation of Hubble's law and the realization that the universe was expanding, a concept that directly supported the Big Bang theory. This discovery shattered the notion of a static universe and introduced the idea that the cosmos had a beginning, igniting debates about its ultimate fate. The mid-20th century saw rapid advancements in observational astronomy and space exploration, culminating in the space age. The launch of Sputnik 1 in 1957 marked the beginning of humanity's direct exploration of space, followed by the Apollo missions that placed humans on the moon in 1969, a testament to human ingenuity and technological prowess. Meanwhile, radio telescopes and satellite observatories unveiled new cosmic phenomena, including quasars, pulsars, and the cosmic microwave background radiation, the latter of which provided strong evidence for the Big Bang model. The concept of the observable universe became increasingly refined, as instruments like the Hubble Space Telescope allowed astronomers to peer deeper into the cosmos than ever before. The observable universe is defined as the region of space from which light has had time to reach us since the beginning of cosmic expansion, approximately 13.8 billion years ago. However, due to the ongoing expansion of space, the actual size of the observable universe extends far beyond 13.8 billion light-years, with estimates suggesting a radius of around 46 billion light-years. This limitation means that beyond a certain point, galaxies recede faster than the speed of light due to cosmic expansion, rendering them forever invisible to us, a humbling realization that underscores the vastness of the cosmos and the limitations of human perception. Modern cosmology has continued to evolve, with the discovery of dark matter and dark energy further complicating our understanding of the universe's composition and fate. Dark matter, inferred through its gravitational effects on galaxies, remains one of the greatest unsolved mysteries in physics, while dark energy, responsible for the accelerated expansion of the universe, challenges our understanding of fundamental forces. Today, humanity stands at the frontier of an unprecedented era in cosmic exploration, with space telescopes like James Webb providing unparalleled views of the early universe, particle physics experiments probing the fundamental building blocks of reality, and ambitious missions aiming to establish a human presence on Mars and beyond. While we have uncovered countless cosmic truths, the universe still holds secrets that elude even our most advanced theories. The journey from ancient stargazers to modern astrophysicists has been one of relentless discovery, yet with every answer comes a new question, reminding us that the cosmos is not just a vast expanse of stars and galaxies, but a living enigma that challenges us to explore, question, and redefine our place within it. The universe is more than a collection of stars, galaxies, and cosmic phenomena. It is a profound reflection of human curiosity, wonder, and existential contemplation. When we gaze into the night sky, we are not merely looking at distant lights. We are staring into the vast unknown, a realm so immense that it renders our personal struggles almost insignificant. Yet it also fills us with awe, humility, and a sense of connection to something far greater than ourselves. The cosmos is not just an abstract scientific subject. It is the ultimate backdrop of our existence, the very fabric within which our lives unfold. It is where we came from, and ultimately, where we will return. The atoms in our bodies were forged in the fiery cores of ancient stars, meaning that every person, every creature, and everything on Earth is literally made of stardust. This realization alone is enough to stir something deep within USA's sense of belonging to the universe, of being an extension of the cosmos itself, woven into its grand narrative. Yet, with wonder comes fear. The universe is beautiful but terrifying, its vastness beyond comprehension. The sheer scale of it is enough to unsettle even the most rational minds as we grapple with questions that have no clear answers. What else is out there? Are we truly alone? What happens after death? And does the cosmos hold any clues? These are not just scientific inquiries. They are deeply emotional questions that strike at the core of what it means to be human. The more we learn, the more we realize how much we do not know. The observable universe stretches over 90 billion light-years in diameter. Yet that is only what we can see beyond that. There may be an infinite expanse, an ocean of galaxies forever beyond our reach. This thought is both humbling and unsettling. It reminds us of our smallness in the grand scheme of things, yet it also emphasizes our uniqueness. On a cosmic scale, our planet is nothing more than a speck of dust in an endless sea of darkness. Yet within this tiny world, we have consciousness, love, dreams, and the ability to question our place in it all. The feeling of insignificance can be overwhelming, especially when contemplating the possibility that humanity is alone in this vast, indifferent universe. The Fermi paradox raises the question of why, despite the high probability of intelligent extraterrestrial life, we have found no evidence of it. Are we truly the only sentient beings in existence? Or is the universe simply too vast for civilizations to cross paths? The silence of space is deafening, evoking a deep existential loneliness. If we are alone, then the responsibility of life itself falls on our shoulders, making our existence even more precious. Yet at the same time, the vast emptiness can feel haunting, as if the universe is a cold, unfeeling void, indifferent to our struggles, our joys, and our fears. This duality, the wonder of existence, and the terror of the unknownness, what makes the cosmos so profoundly emotional. It is a mirror that reflects back our deepest anxieties and aspirations. But the unknown is not just frightening, it is also exhilarating. The idea that we are still at the beginning of our cosmic journey, that there are endless mysteries yet to be unraveled, ignites a deep sense of adventure. The discovery of exoplanets, inhabitable zones, the possibility of microbial life beneath the icy surfaces of moons like Europa and Enceladus, the hunt for signals from intelligent civilizations. These pursuits are not just about science, they are about hope. Hope that we are part of a greater cosmic story, that there is more to existence than what we see, that our journey has only just begun. Every time a new telescope captures a distant galaxy, every time we send a probe to explore a new world, every time we push the boundaries of what is known, we are affirming that human curiosity is limitless. Personal curiosity is what drives people to look up at the stars and wonder about their place in the grand scheme of things. It is the same curiosity that has driven explorers across oceans, artists to create masterpieces, and philosophers to ponder the meaning of life. The universe is, in many ways, the ultimate mystery, and it calls to us in ways that are difficult to articulate. Some find solace in the idea that, in the vastness of space, their personal worries are minuscule. Others find meaning in the knowledge that, despite our cosmic insignificance, we have the ability to seek answers, to create, to love, to dream. In the end, the universe is not just out there, it is within us, shaping our thoughts, our emotions, and our very sense of self. There is something deeply poetic about the fact that the universe, a place of chaos, explosions, and seemingly random cosmic events, has produced beings capable of contemplating it. The greatest paradox is that we are the universe trying to understand itself, a collection of atoms arranged in such a way that we can question the nature of reality. This is why people should care about the cosmos, not because it is distant and mysterious, but because it is intimately tied to who we are. Every human emotion, from love to despair, from curiosity to fear, is reflected in the grand story of the universe. The wonder of existence and the fear of the unknown are two sides of the same coin, and it is this interplay that makes our exploration of the cosmos not just a scientific endeavor, but an emotional one. As we stand on the precipice of a new era of discovery, with missions planned to explore Mars, telescopes peering deeper into time, and physicists attempting to unlock the mysteries of dark matter and dark energy, we must remember that our drive to understand the universe is not just about knowledge, it is about meaning. Every star in the night sky represents a story yet to be told, a world yet to be explored, a possibility yet to be realized. This is why space captivates. Use it is not just about what is out there, but what it tells us about ourselves. The universe is a story, and we are part of it. Whether that story is one of solitude or connection, of discovery or existential dread, is still unfolding. But one thing remains certain. As long as there are questions to be asked, as long as there are mysteries to be solved, we will continue to look to the stars, seeking answers, seeking understanding, seeking a sense of place in the grandest of all narratives. The universe is not just something we observe, it is something we are part of, something that challenges us to think beyond the boundaries of our everyday experience. It is a vast, enigmatic, and ever-expanding frontier that forces us to confront the biggest questions imaginable. What is reality? What is time? Where did we come from? And where are we going? These are not abstract scientific inquiries. They are fundamental to how we understand ourselves, our existence, and our place in the cosmos. The universe does not simply exist as an isolated entity. It shapes the very fabric of our reality, influencing the way we perceive time, space, and even life itself. And yet, despite all we have learned, the vast majority of it remains a mystery. This is what makes the cosmos so compelling, so exhilarating, and at times, so terrifying. But it also presents an opportunity and invitation to engage, to question, to wonder, and most importantly, to participate in the conversation about the greatest unknowns that surround us. Consider the nature of time. We experience it linearly, moving from past to future. Yet modern physics suggests that time may not be as simple as it seems. Einstein's theory of relativity tells us that time is not an absolute, but rather a dimension, intertwined with space itself, bending and stretching under the influence of gravity. If time can be altered by cosmic forces, then what does that mean for our perception of reality? Could time travel ever be possible? And if so, what implications would that have on free will, causality, and even the structure of the universe itself? The very thought of bending time challenges everything we know about existence. If past, present, and future are not as rigid as they seem, then how do we define our place in the flow of reality? If time itself is an illusion, then what does it mean to be alive in a single moment? These questions do not just belong to physicists, they belong to all of us, as they shape the way we interpret the fundamental nature of our existence. Then, there is the question of dark matter and dark energy, two invisible forces that make up roughly 95% of the universe, yet remain utterly mysterious to us. If these forces control the structure and fate of the cosmos, then how can we claim to truly understand reality? We pride ourselves on knowledge, on science, on our ability to observe, analyze, and predict the laws of nature, and yet nearly everything we can see, touch, and measure accounts for only a tiny fraction of what is actually out there. This realization is not just a scientific curiosity, is a humbling confrontation with the limits of human perception. What if dark matter is not just some missing particle, but an entirely different aspect of reality, something we have not yet evolved the capacity to comprehend? What if dark energy reveals an underlying force of the universe that could one day be harnessed, fundamentally altering our understanding of physics? These unknowns are not just technical problems for researchers. They represent a profound gap in our understanding of the cosmos, and therefore, a gap in our understanding of ourselves. Imagine if one of these mysteries were solved in our lifetime. Imagine waking up one day to the news that scientists have finally identified what dark matter is, unlocking a deeper layer of the universe's structure. Imagine the possibility that we could manipulate space-time in ways we never thought possible, leading to a future where interstellar travel is no longer a fantasy, but a reality. Consider the impact of discovering extraterrestrial life, not just bacteria on another planet, but intelligent civilizations capable of communication. How would that change everything we know about ourselves, our place in the cosmos, our philosophies, our religions, our collective sense of identity? Would it unite humanity in the realization that we are not alone? Or would it divide us in fear and uncertainty? Would it reinforce the idea that life is inevitable throughout the universe? Or would it raise new questions about why civilization seems so rare? These possibilities are not just speculative, they are within reach. With advancements in space exploration, new telescopes capable of detecting Earth-like planets, and the growing understanding of biology in extreme environments, we are closer than ever to answering the question that has haunted us for centuries. Are we alone? But even if we never find extraterrestrial life, even if the answers to dark matter, dark energy, and the nature of time remain elusive for centuries to come, the mere act of searching shapes who we are. Science is not just about reaching conclusions. It is about the journey of inquiry, the thrill of the unknown, the endless pursuit of knowledge that stretches the limits of our imagination. The cosmos is not static, it is a living enigma, one that continuously evolves and surprises us. Every new discovery changes the way we see ourselves. Every photograph of a distant galaxy taken by telescopes like James Webb is a glimpse into the past, showing us light that has traveled for billions of years to reach us. When we look at those images, we are not just seeing distant stars, we are witnessing the history of the universe unfold before our eyes. How can one not feel a sense of awe at the realization that we are looking back in time, that the light from those galaxies predates humanity itself? This is not just science. This is poetry, a grand cosmic narrative in which we are both spectators and participants. So, why should you care? Because the universe is not separate from you, is part of you. Every breath you take, every thought that crosses your mind, every experience you have is possible because of the laws of physics, the fundamental forces that govern reality. When you look at the stars, you are looking at the past, at the remnants of ancient celestial events that shaped the very elements within your body. When you ponder the vastness of space, you are engaging in the same existential questions that have driven humanity forward for thousands of years. And when you question reality itself, you are stepping into a tradition of thinkers, dreamers, and explorers who have dared to push beyond the limits of what was once thought possible. Now, the conversation is yours to continue. What do you think about the mysteries of the universe? What questions keep you up at night? Do you believe we are alone in the cosmos? Or do you think intelligent life exists somewhere out there, waiting to be discovered? How do you feel about the idea that time might not be as fixed as it seems? Do you think dark matter and dark energy are simply undiscovered particles? Or could they be something even more profound, evidence of hidden dimensions, alternate realities, or entirely new laws of physics? And how do these ideas make you feel? Do they fill you with wonder, with fear, with curiosity, or with a deep appreciation for the vastness of existence? This is not just a scientific discussion, it is a human one. It is a conversation about what it means to be aware, to be conscious, to seek meaning in an infinite cosmos that neither confirms nor denies our place within it. Whether we are alone or one of many, whether we understand the universe fully or remain forever in the dark, one thing remains clear. The act of questioning, of exploring, of seeking answers is what defines us. The universe may be silent, but our minds are loud with wonder. It is up to us to continue the conversation, to push the boundaries of knowledge, to never stop asking, never stop searching, and never stop embracing the beauty of the unknown. So, what do you think? Where does the journey of discovery lead next? And most importantly, are you ready to be part of the story? The universe stretches before us like an endless ocean of darkness, punctuated by islands of light galaxies, nebulae, and stars burning like distant beacons in the void. It is a place both haunting and mesmerizing, where time itself bends under the weight of immense gravitational forces, and where the very fabric of reality ripples with cosmic events beyond human comprehension. If one were to drift through intergalactic space, far from the warmth of our Sunday and the familiarity of the Milky Way, there would be nothing but silentian, infinite, inescapable silence that speaks to the staggering emptiness of the cosmos. And yet, within that darkness, there is life, movement, and a grand narrative unfolding across billions of years. The story of the universe is not one of stillness, but of creation and destruction, of galaxies colliding in slow-motion ballets, of stars being born in brilliant clouds of gas, and of black holes swallowing entire worlds into their unseen depths. Picture the birth of a galaxy, clouds of gas and dust collapsing under gravity's relentless pull, condensing over millions of years until the first stars ignite, their fusion-powered hearts blazing with the energy to illuminate the abyss. These stellar nurseries, sculpted by radiation and violent winds, give rise to systems of planets orbiting their parent stars, some perhaps harboring conditions similar to our own world. Imagine a newly formed exoplanet, a blue marble adrift in the vastness of space, its atmosphere rich with the chemical potential for life. Could it be that on one such world, light years away, intelligent beings gaze up at their sky and wonder, just as we do, if they are alone? Not all places in the universe are welcoming to life. Between galaxies lie the great cosmic void cements, unfathomable regions of near absolute emptiness, where the density of matter is so low that one could travel for millions of years without encountering a single star. These voids, stretching hundreds of millions of light years across, are the silent cathedrals of the cosmos, where the darkness reigns supreme, broken only by the faint, ghostly glow of faraway galaxies at their periphery. What forces sculpted these desolate regions? What hidden physics governs the unseen currents of dark matter threading through them, shaping the very structure of the universe? Dark matter is one of the most perplexing entities in modern physics, an invisible substance that makes up most of the universe's mass, yet refuses to reveal itself to direct observation. We cannot see it, nor can we touch it, but we know it is there because of the way galaxies move. Without dark matter, the outer stars of spiral galaxies should drift away, flung outward by their own speed, and yet they remain bound, as if held in place by an invisible hand. This unknown force, this ghostly presence, surrounds us, permeates space, and governs the dance of the cosmos, yet we have no idea what it truly is. Is it composed of undiscovered particles? Is it the manifestation of a deeper, hidden aspect of gravity that we do not yet understand? Or is it something even stranger, a clue to an entirely new form of physics that lies just beyond our grasp? There is no shortage of brilliant minds attempting to unravel these mysteries. Throughout history, humanity has been guided by those who dared to challenge the unknown, who looked at the sky not with fear, but with curiosity. Copernicus shattered the illusion of an Earth-centered universe. Galileo turned his telescope to the heavens and saw the imperfect, dynamic reality of the cosmos, and Newton uncovered the forces that governed the celestial dance. In the 20th century, Albert Einstein rewrote our understanding of space and time, revealing that gravity is not merely a force, but a curvature in the very fabric of reality itself. His general theory of relativity predicted phenomena so bizarre that even he doubted their physical reality: black holes, gravitational waves, and the expansion of the universe. And yet, with time, these predictions have been confirmed, reshaping our understanding of existence itself. Edwin Hubble, through careful observation of distant galaxies, made one of the most profound discoveries in human history: realization that the universe is expanding. His work, measuring the redshift of galaxies, led to the inescapable conclusion that space itself was stretching, carrying galaxies away from one another. This discovery gave birth to the Big Bang Theory, the idea that everything we see, the stars, the galaxies, the voids, and even time itself originated from a single point, a moment of unimaginable density and energy that set the cosmos into motion. But the work did not stop there. In the 21st century, cosmologists such as Vera Rubin furthered our understanding of dark matter, while the discovery of dark energy, an even more mysterious force driving the acceleration of cosmic expansion, has deepened the puzzle of what the universe is truly made of. As we stand at the precipice of new discoveries, the tone of scientific exploration is one of both awe and frustration. Every new answer leads to another question. The launch of the James Webb Space Telescope has allowed us to peer further into the past than ever before, capturing light from the first galaxies formed in the wake of the Big Bang. Yet, even as we gather more data, anomalies emerge: galaxies that should not exist, structures that should not have formed so early, patterns that challenge the models we have relied on for decades. What does it all mean? Is the universe trying to tell us something, to hint at a deeper truth just beyond our reach? The excitement of discovery is tinged with the realization that we may never fully comprehend the cosmic story unfolding around us. There is something humbling about that, about the idea that we, small beings on a small planet, are trying to grasp the workings of a cosmos that has existed for billions of years and will continue long after we are gone. And yet, we persist. We build instruments to see the unseeable, to measure the immeasurable. We collide particles at near-light speed in search of the fundamental building blocks of reality. We send probes beyond our solar system, carrying messages in the hope that one day, something will find them. We search for signs of intelligent life, listening for a whisper in the cosmic silence. The pursuit of knowledge is not just a scientific endeavor, it is an emotional one. The universe is a source of wonder, a place of infinite possibilities and unsolved mysteries. It is vast and indifferent, yet it is also deeply personal. It forces us to confront the biggest questions of all: who are we, where did we come from, and what does it all mean? The answers may not come in our lifetime. Some may never come at all, but that does not matter. What matters is that we continue to ask, to seek, to wonder, because as long as we do, we remain connected to the greatest mystery of all, the endless, unfolding story of the universe. The universe stretches before us like an endless ocean of darkness, punctuated by islands of light galaxies, nebulae, and stars burning like distant beacons in the void. It is a place both haunting and mesmerizing, where time itself bends under the weight of immense gravitational forces, and where the very fabric of reality ripples with cosmic events beyond human comprehension. If one were to drift through intergalactic space, far from the warmth of our Sunday and the familiarity of the Milky Way, there would be nothing but silentian, infinite, inescapable silence that speaks to the staggering emptiness of the cosmos. And yet, within that darkness, there is life, movement, and a grand narrative unfolding across billions of years. The story of the universe is not one of stillness, but of creation and destruction, of galaxies colliding in slow-motion ballets, of stars being born in brilliant clouds of gas, and of black holes swallowing entire worlds into their unseen depths. Picture the birth of a galaxy: clouds of gas and dust, collapsing under gravity's relentless pull, condensing over millions of years until the first stars ignite, their fusion-powered hearts blazing with the energy to illuminate the abyss. These stellar nurseries, sculpted by radiation and violent winds, give rise to systems of planets orbiting their parent stars, some perhaps harboring conditions similar to our own world. Imagine a newly formed exoplanet, a blue marble adrift in the vastness of space, its atmosphere rich with the chemical potential for life. Could it be that on one such world, light years away, intelligent beings gaze up at their sky and wonder, just as we do, if they are alone? Not all places in the universe are welcoming to life. Between galaxies lie the great cosmic void cements, unfathomable regions of near absolute emptiness, where the density of matter is so low that one could travel for millions of years without encountering a single star. These voids, stretching hundreds of millions of light years across, are the silent cathedrals of the cosmos, where the darkness reigns supreme, broken only by the faint, ghostly glow of faraway galaxies at their periphery. What forces sculpted these desolate regions? What hidden physics governs the unseen currents of dark matter threading through them, shaping the very structure of the universe? Dark matter is one of the most perplexing entities in modern physics, an invisible substance that makes up most of the universe's mass, yet refuses to reveal itself to direct observation. We cannot see it, nor can we touch it, but we know it is there because of the way galaxies move. Without dark matter, the outer stars of spiral galaxies should drift away, flung outward by their own speed, and yet they remain bound, as if held in place by an invisible hand. This unknown force, this ghostly presence, surrounds us, permeates space, and governs the dance of the cosmos, yet we have no idea what it truly is. Is it composed of undiscovered particles? Is it the manifestation of a deeper, hidden aspect of gravity that we do not yet understand? Or is it something even stranger, a clue to an entirely new form of physics that lies just beyond our grasp? There is no shortage of brilliant minds attempting to unravel these mysteries. Throughout history, humanity has been guided by those who dared to challenge the unknown, who looked at the sky not with fear, but with curiosity. Copernicus shattered the illusion of an Earth-centered universe. Galileo turned his telescope to the heavens and saw the imperfect, dynamic reality of the cosmos. And Newton uncovered the forces that govern the celestial dance. In the 20th century, Albert Einstein rewrote our understanding of space and time, revealing that gravity is not merely a force, but a curvature in the very fabric of reality itself. His general theory of relativity predicted phenomena so bizarre that even he doubted their physical reality: black holes, gravitational waves, and the expansion of the universe. And yet, with time, these predictions have been confirmed, reshaping our understanding of existence itself. Edwin Hubble, through careful observation of distant galaxies, made one of the most profound discoveries in human history: realization that the universe is expanding. His work, measuring the redshift of galaxies, led to the inescapable conclusion that space itself was stretching, carrying galaxies away from one another. This discovery gave birth to the Big Bang Theory, the idea that everything we see, the stars, the galaxies, the voids, and even time itself originated from a single point, a moment of unimaginable density and energy that set the cosmos into motion. But the work did not stop there. In the 21st century, cosmologists such as Vera Rubin furthered our understanding of dark matter, while the discovery of dark energy, an even more mysterious force driving the acceleration of cosmic expansion, has deepened the puzzle of what the universe is truly made of. As we stand at the precipice of new discoveries, the tone of scientific exploration is one of both awe and frustration. Every new answer leads to another question. The launch of the James Webb Space Telescope has allowed us to peer further into the past than ever before, capturing light from the first galaxies formed in the wake of the Big Bang. Yet even as we gather more data, anomalies emerge, galaxies that should not exist, structures that should not have formed so early, patterns that challenge the models we have relied on for decades. What does it all mean? Is the universe trying to tell us something? To hint at a deeper truth just beyond our reach? The excitement of discovery is tinged with the realization that we may never fully comprehend the cosmic story unfolding around us. There is something humbling about that, about the idea that we, small beings on a small planet, are trying to grasp the workings of a cosmos that has existed for billions of years and will continue long after we are gone. And yet, we persist. We build instruments to see the unseeable, to measure the immeasurable. We collide particles at near-light speed in search of the fundamental building blocks of reality. We send probes beyond our solar system, carrying messages in the hope that one day, something will find them. We search for signs of intelligent life, listening for a whisper in the cosmic silence. The pursuit of knowledge is not just a scientific endeavor, it is an emotional one. The universe is a source of wonder, a place of infinite possibilities and unsolved mysteries. It is vast and indifferent, yet it is also deeply personal. It forces us to confront the biggest questions of all. Who are we? Where did we come from? And what does it all mean? The answers may not come in our lifetime. Some may never come at all. But that does not matter. What matters is that we continue to ask, to seek, to wonder. Because as long as we do, we remain connected to the greatest mystery of all, the endless, unfolding story of the universe. The quest to find the true edge of the universe, to grasp the ultimate nature of reality, has driven human curiosity for millennia. Yet the deeper we look into the cosmos, the more elusive the answers become. Every new discovery brings with it paradoxes, contradictions, and limits to what we can observe or even comprehend. It is as if the universe itself resists being fully understood, an ever-receding horizon where the answers to our greatest questions remain just out of reach. While we have uncovered astonishing truths about the cosmos, its origins, its expansion, and its intricate web of galaxies, there is growing evidence to suggest that we may never find its true edge, or even determine whether such a boundary exists at all. One of the most unsettling realizations in modern physics is that the observable universe is not the full extent of existence. What we see, mapped by telescopes and measurements of cosmic radiation, is limited by the speed of light and the age of the universe. Beyond this visible horizon, space itself continues to expand at an accelerating rate, meaning that vast regions of the cosmos are forever beyond our reach. No matter how advanced our instruments become, no matter how far we peer into the depths of space, there will always be a fundamental barrier to what we can detect. Even if we could travel at the speed of light, much of the universe would remain inaccessible, its distant galaxies receding faster than any spacecraft could ever hope to follow. The very laws of physics conspire against our ability to explore the full breadth of reality, hinting that the universe may be infinite in scope, or worse, entirely unknowable beyond a certain point. The paradoxes in physics further complicate this quest. At the heart of modern cosmology lies an unresolved conflict between quantum mechanics and general relativity. Einstein's equations describe space and time as a smooth, continuous fabric that bends under the influence of mass and energy. But on the smallest scales, quantum theory reveals a universe governed by randomness, uncertainty, and particles that flicker in and out of existence. These two pillars of modern physics, both experimentally verified and highly successful in their own domains, are fundamentally incompatible with one another. When we attempt to merge them, contradictions arise of predictions that make no sense, infinities that break the mathematical framework of physics itself. The very nature of space-time at the Planck scale, the smallest conceivable unit of measurement, remains a mystery. Does space itself dissolve into a quantum foam? An ocean of fluctuating probabilities where the concept of location loses meaning? If so, what does that imply about the structure of the universe at its deepest level? Could there be layers of reality hidden within dimensions we cannot access? Or laws of physics yet to be discovered that redefine everything we think we know? Another troubling sign that we may never reach a final understanding is the presence of observational constraints that prevent us from fully testing our theories. Even the Big Bang, the most widely accepted explanation for the origin of the universe, remains incomplete. We can trace cosmic history back to a fraction of a second after its beginning, when space was a hot, dense plasma. But the true moment of creation, if such a moment even exists, remains hidden behind a veil of physics we cannot yet penetrate. The cosmic microwave background radiation, the faint glow left over from the early universe, provides a snapshot of conditions nearly 14 billion years ago. But before that time, the universe was opaque to light, making it impossible for us to see further back. Could there be a deeper history, a pre-Big Bang reality that exists beyond our reach? Some theories suggest that our universe is just one bubble in a multiverse, a vast sea of parallel realities that obey different physical laws. If this is true, then much of existence may forever be beyond our ability to detect or understand. The limitations of observation extend beyond the cosmic horizon. Even within the known universe, our ability to measure and predict is bound by the constraints of physics and technology. The search for dark matter, for example, remains one of the most perplexing challenges in modern science. We infer its presence through gravitational effects, yet every attempt to directly detect dark matter particles has failed. What if dark matter is not made of particles at all? What if our entire framework for understanding gravity is flawed, requiring a radical revision of our most fundamental theories? The same is true for dark energy, the mysterious force driving the accelerated expansion of the universe. We know it exists, yet we do not know why, and current models offer little insight into its true nature. Could it be a property of empty space itself, a vacuum energy that defies conventional physics? Or does it suggest the influence of an unknown force, something completely outside our current understanding of reality? These unanswered questions raise an unsettling possibility. What if some aspects of the universe are simply unknowable, beyond the reach of human comprehension? Compounding these issues is the ever-changing nature of scientific knowledge itself. The history of cosmology is one of shifting paradigms, where each breakthrough replaces old theories with new ones. The geocentric model, once the absolute truth, gave way to heliocentrism. Newtonian gravity, long considered unshakable, was eventually superseded by Einstein's relativity. Today's models our understanding of black holes, quantum fields, and cosmic expansion are likely incomplete or even fundamentally incorrect in ways we have yet to realize. This does not mean that science is failing. Rather, it reveals the endless nature of discovery. Yet it also suggests that any notion of a final, complete understanding of the universe may be a mirage, something always shifting as new evidence emerges. Even if we someday achieve a theory of everything, a single framework uniting all forces of nature, it may only raise further questions. What lies beyond our universe? Is the fabric of reality itself emergent from deeper principles we cannot yet fathom? If we find the edge of the observable universe, is it truly an edge or merely a threshold to something greater? The conflict we face in cosmology is not just scientific, it is philosophical. It forces us to confront the possibility that the ultimate nature of existence may be forever beyond us, not because we lack intelligence or technology, but because the structure of the universe itself may be built in a way that prevents total understanding. Yet, despite all of this, the pursuit of knowledge continues. We build more powerful telescopes, refine our models, and seek deeper truths, not because we expect to find a final answer, but because the act of questioning itself is what defines us as a species. Even if we never reach the true edge of the universe, the journey itself filled with wonder, paradox, and discovers what matters. Perhaps the greatest revelation of all is not the universe's edge, but the realization that the search for it will never truly end. The universe is an arena of constant tension, not just in the cosmic forces at play, but also in the very ideas that seek to explain its origins, structure, and limits. For centuries, scientists have wrestled with competing theories, struggling to define the edge of the cosmos if such a boundary even exists. The very notion of an edge is fraught with paradoxes, challenging both our observational capabilities and the mathematical models that underpin our understanding of reality. What does it mean for the universe to be finite or infinite? If it has a boundary, what lies beyond? If it is truly boundless, how can we ever hope to measure, conceptualize, or even comprehend it? These are the questions that fuel the ongoing struggle among cosmologists, a conflict between observation and theory, between the known and the unknowable. One of the central tensions in modern cosmology is the clash between the infinite and finite universe models. If the universe is finite, then it must have some kind of boundary, even if that boundary is beyond our reach. But what happens at the edge? Is there an actual wall of sorts? Or does space curve back on itself, forming a closed system like the surface of a sphere? Some theories suggest that if we could travel far enough in one direction, we might eventually return to our starting point, much like navigating a globe. This concept of a closed universe is mathematically sound, yet it conflicts with other models that propose an infinite, ever-expanding cosmos. If the universe is infinite, then it has no boundary yet. This raises another paradox. If it has been expanding since the Big Bang, how can it already be infinite? Wouldn't it have started as something finite and simply grown ever larger? The contradiction seems impossible to resolve, and yet both possibility finite or infinite introduce complications that neither theory has been able to fully reconcile. Adding to this struggle is the tension between what we observe and what theoretical physics predicts. The observable universe, the region of space from which light has had time to reach us, is vast but not unlimited. We estimate its radius at about 46 billion light-years. But this does not mean that space ends there. It merely marks the limit of what we can detect. Beyond that horizon, galaxies and structures likely exist, but they are moving away from us so quickly due to cosmic expansion that their light will never reach us. This observable limit creates a fundamental problem. If we can only see a fraction of what exists, how can we ever claim to know the true nature of the whole? What if the cosmos behaves differently beyond our observational reach, governed by unknown laws or forces we cannot detect? This conflict has led some physicists to argue that cosmology itself is inherently limited, that we may never be able to answer certain fundamental questions because the data we need is forever inaccessible. Even within the realm of observable data, inconsistencies emerge. One of the biggest tensions in modern cosmology is the disagreement over the Hubble constant, which describes the rate of cosmic expansion when measured using different methods, one based on the cosmic microwave background radiation and another based on the movements of galaxies. The values do not match. This discrepancy, known as the Hubble tension, suggests that something is missing in our understanding of the universe's expansion. Is dark energy behaving differently than expected? Are our calculations flawed? Or is there an entirely new aspect of physics that we have yet to discover? The conflict between these measurements is more than just a minor error. It is a fundamental crisis that calls into question the reliability of our cosmic models. Then there is the issue of dark matter and dark energy, two invisible forces that dominate the universe, but remain poorly understood. Dark matter is thought to provide the extra gravitational pull that holds galaxies together, while dark energy is responsible for pushing the universe apart at an accelerating rate. The problem? We have never directly detected either one. Dark matter is inferred only through gravitational effects, and all attempts to identify its particles have failed. Dark energy is even more mysterious, a force with no clear explanation beyond mathematical necessity. Some physicists argue that these concepts are merely placeholders for deeper, yet-to-be-discovered laws of nature. Others insist that dark matter and dark energy are real, but exist in forms we have yet to uncover. The lack of direct evidence creates a schism within the scientific community. Are we simply looking in the wrong way? Or have we fundamentally misunderstood the nature of the universe? This conflict extends into the realm of quantum mechanics and general relativity, two foundational theories that, despite their success, refuse to work together. Quantum mechanics describes the behavior of particles on the smallest scales, where uncertainty and probability rule, while general relativity explains the large-scale structure of the universe, where gravity dominates. The problem arises when we try to apply both theories to extreme environments, such as black holes or the early moments of the Big Bang. The equations break down, producing nonsensical infinities. This suggests that our understanding of reality is incomplete, that there must be a deeper, unifying theory, perhaps a quantum theory of gravity, that can bridge the divide. Yet, despite decades of effort, no such theory has emerged. String theory, one of the leading candidates, proposes that all particles are tiny vibrating strings existing in multiple dimensions, but it remains unproven and controversial. Other models, such as loop quantum gravity, attempt to reconstruct space-time in a fundamentally different way, but they too lack empirical confirmation. The divide between these competing approaches highlights a deeper truth: no single model has yet succeeded in fully describing the universe. Beyond theoretical conflicts, there is the question of whether the universe itself prevents us from ever fully understanding it. The more we learn, the more barriers we encounter. The cosmic censorship hypothesis suggests that singularities, points where gravity becomes infinite, such as in black holes, are always hidden from view, preventing us from ever directly studying them. If true, this would mean that the most extreme environments in the universe, where physics itself may break down, will always be beyond our reach. Similarly, the existence of cosmic event horizons means that certain regions of space are forever cut off from observation. Some physicists argue that the very nature of reality might be fundamentally unknowable, that there are limits to human comprehension, just as there are limits to physical observation. Even if we could access more data, even if new discoveries reshape our understanding, there is the deeper philosophical conflict. Can we ever claim to know the truth about the universe? Every scientific model is just that, a model, an approximation based on limited data. History has shown that theories once considered absolute truths are eventually overturned. The steady march of science is a process of refinement, but it also means that what we accept today as fundamental knowledge may one day be replaced. If this cycle continues indefinitely, does that mean a final, complete theory of the universe is impossible? Will we always be chasing an answer that remains just out of reach? The struggle to define the edge of the universe, to determine whether it is finite or infinite, to reconcile quantum mechanics with general relativity, to understand dark matter and dark energy, and to resolve the inconsistencies in observational data. These are not separate battles, but interconnected conflicts that drive modern cosmology. Each question leads to another, each answer creates new paradoxes, and each theory competes for dominance in an ever-shifting landscape of knowledge. The universe is not simply a puzzle to be solved, but a vast, evolving mystery that challenges us to rethink our assumptions at every turn. And yet, despite the conflicts, the contradictions, and the seemingly insurmountable obstacles, the search continues. Cosmologists, physicists, and astronomers push forward, not because they expect to find all the answers, but because the pursuit of understanding itself is what defines us. The universe may never reveal all of its secrets. There may always be an edge beyond which we cannot see, a question we cannot answer, a force we cannot detect. But as long as we continue to explore, as long as we continue to ask, the conflict is not a defeat, it is the very essence of discovery. If the universe has no edge, the consequences stretch far beyond scientific curiosity. They redefine our understanding of reality, challenge our deepest assumptions about existence, and force us to confront the limits of human comprehension. A boundless universe, one without a final boundary, without an ultimate limit, raises profound questions, not only for cosmology, but also for physics, philosophy, and our place in the cosmos. If there is no edge, then where does the universe end? Or does it truly go on forever, extending infinitely in all directions, an endless expanse of galaxies, voids, and cosmic structures beyond anything we could ever observe? And if the universe is infinite, what does that mean for the nature of space, time, and even consciousness itself? The implications for physics and cosmology are staggering. An infinite universe upends our most fundamental assumptions about the structure of reality. If space goes on forever, then every possible arrangement of matter, every possible configuration of stars and galaxies, must eventually repeat somewhere in the vastness of existence. This idea, known as the infinite repetition hypothesis, suggests that if one were to travel far enough, though likely an impossible distance zone, might find another version of Earth, another version of oneself, living a slightly different life. This is not just science fiction, it is a logical consequence of infinity. The very laws of probability dictate that in an infinite system, patterns must inevitably repeat, meaning that countless variations of every possible event are playing out somewhere in the cosmos. This realization fractures our sense of uniqueness, forcing us to consider whether individuality is an illusion, whether our consciousness is just one instance among countless others scattered across the infinite expanse. More fundamentally, an infinite universe challenges the standard models of cosmology. If space is truly infinite, then the Big Bang, the moment we consider the origin of everything, must be reinterpreted. Our current understanding is that the universe began as a singularity, an infinitely dense point that expanded into the cosmos we see today. But how can an infinite universe emerge from a singularity? If space already extended infinitely before the Big Bang, Then what exactly was expanding? Did the Big Bang not create space itself, but merely rearrange an already infinite expanse of reality? Some theories suggest that the Big Bang was not the beginning but just one of many cosmic events in an eternally evolving universe, where cycles of expansion and contraction, birth and rebirth, stretch back indefinitely into the past. This aligns with models such as the cyclic universe or the multiverse hypothesis, where our universe is merely one among countless others, each with its own unique laws of physics. The existence of an infinite universe would also demand new physics beyond our current models. The laws we rely on, general relativity, quantum mechanics, and the standard model of particle physics, are built around a universe with observable limits. But in an infinite cosmos, how can we define a center or an edge? How does causality function in a system that has no boundary? Could there be areas of space where the known laws of physics simply break down, or where entirely new forces govern reality? Some physicists argue that an infinite universe is best explained through the existence of additional dimensions beyond the familiar three of space and one of time. String theory, for example, suggests that our universe is part of a higher dimensional structure, where other branes, higher dimensional spaces, may exist parallel to ours, separated by distances we cannot perceive. If true, this would mean that what we think of as the universe is merely a slice of a much grander reality, with the true nature of existence extending far beyond what we can currently measure. The philosophical and existential implications of an infinite universe are even more profound. If there is no edge, no final frontier, then what does that mean for human purpose? For centuries, we have sought meaning in the idea of a finite cosmos, one that we could eventually map, explore, and understand. But if the universe is truly without limit, then the idea of discovery itself becomes an eternal process, an unending journey with no final destination. What does it mean to search for truth in a reality where there is no ultimate answer? Is knowledge always incomplete, forever evolving? This question echoes the deepest struggles of philosophy and metaphysics. The idea that reality itself may be beyond full comprehension is both exhilarating and terrifying. It suggests that our greatest scientific achievements may only be the beginning of an eternal pursuit, a quest with no conclusion. Moreover, an infinite universe erases the comforting notion of a single contained reality. If space is boundless, then time itself may also be infinite, meaning that there was no true beginning and that there will be no true end. This undermines many traditional conceptions of creation and existence. In religious and philosophical traditions, the idea of a cosmic beginning, a moment of creation, a starting point thus, provided a framework for understanding our place in the universe. But an infinite cosmos eliminates this starting point, suggesting instead that existence simply is, without origin, without purpose beyond what we assign to it. Does this diminish our significance, or does it elevate it? If the universe has no edge, then we are not in a special position within it. We are simply part of an endless tapestry of matter, energy, and consciousness. But at the same time, this realization means that existence itself is rare and precious, a fleeting moment in the vast infinity of time. The infinite universe hypothesis also brings into question the nature of reality itself. If the cosmos is truly boundless, then what prevents the existence of infinite versions of ourselves, infinite Earths, infinite histories, playing out with every possible variation? If every possibility exists somewhere in the infinite expanse, then how do we define what is real? Is our experience of life just one among an uncountable number of possibilities? This ties into the many worlds interpretation of quantum mechanics, which suggests that every quantum event branches into multiple realities, creating a vast network of parallel existences. If the universe is infinite, then it is not just space that extends without limit, it is also possibility, meaning that every choice we make, every moment we experience, exists in an infinite web of variations. This concept, while theoretically possible, challenges our very notion of identity. Are we individuals, or are we just one of many instances of the same consciousness experiencing different realities? On a more practical level, the idea of an infinite universe affects the way we approach science itself. If the cosmos is boundless, then no single theory can ever fully describe it. Every model we create is just an approximation, a temporary framework that works within a limited observable region. This means that scientific progress will always be asymptotic. We may get closer to understanding the truth, but we will never reach a final, complete theory. This requires a shift in mindset, moving away from the idea of ultimate answers and embracing the idea that discovery is a continuous, evolving process. In an infinite universe, science itself is infinite, always expanding, always refining, never truly complete. The need for new physics in such a reality is undeniable. If the universe has no edge, then we must rethink the way we define space, time, and matter. General relativity and quantum mechanics, while successful in their respective domains, may only be approximations of a deeper, more fundamental theory that remains undiscovered. Some physicists believe that a theory of quantum gravity, a framework that unifies the laws of the large with the laws of the small, may provide the answers. Others speculate that entirely new forces or dimensions may be required to explain an infinite cosmos. If the universe is truly boundless, then our understanding of it must also be boundless, always evolving, always adapting. In the end, the question of whether the universe has an edge is more than just a scientific puzzle. It is a challenge to our very way of thinking. It forces us to confront the limits of knowledge, the nature of reality, and the meaning of existence. Whether finite or infinite, the cosmos remains a vast, mysterious, and awe-inspiring frontier, one that invites us to explore, to question, and to wonder. And perhaps that is the true consequence of an infinite universe, that we will ever fully understand it, but that the journey of discovery will never truly end. The journey of understanding the universe has been marked by moments of profound revelation, turning points, where scientific discoveries reshaped our fundamental perceptions of reality. While ancient astronomers once believed the cosmos to be a finite realm centered around Earth, we now recognize it as a vast, ever-expanding structure shaped by forces beyond our immediate comprehension. In recent decades, a series of key scientific breakthroughs have forced us to confront new cosmic mysteries, challenging our assumptions and expanding the horizon of what is possible. These revelations have not only redefined our knowledge of space and time, but have also set the stage for a new era of exploration driven by dark energy, advanced technology, and unexpected findings from cutting-edge telescopes. One of the most dramatic turning points in modern cosmology came in 1998 with the discovery of dark energy, an invisible force driving the accelerated expansion of the universe. Before this discovery, scientists largely believed that the universe's expansion, set in motion by the Big Bang, would eventually slow due to gravitational attraction. Some hypothesized that expansion might even halt, leading to a potential Big Crunch scenario in which the universe would collapse back into itself. However, observations of distant supernovae using the Hubble Space Telescope revealed something shocking. Rather than slowing down, the expansion of the universe was accelerating. This meant that some unknown force was acting against gravity, stretching space at an ever-increasing rate. The nature of dark energy remains one of the greatest unsolved mysteries in physics, comprising approximately 68% of the universe's total energy content, yet defying all known forms of detection and measurement. The discovery of dark energy forced a complete re-evaluation of our understanding of cosmic evolution. If expansion continues unchecked, the universe could end in a big freeze, where galaxies drift further apart until all matter becomes isolated, leading to a dark, empty, and lifeless cosmos. Alternatively, dark energy's effects might change over time, potentially leading to a big rip, where even atomic structures are torn apart by an overwhelming force. These possibilities highlight the enormous influence dark energy has on shaping the fate of the universe, an influence we still struggle to fully comprehend. Could dark energy be linked to vacuum energy, an inherent property of empty space? Is it connected to undiscovered particles, or an entirely new field of physics? Some theories propose that dark energy is a sign of deeper dimensions, or that it is evidence of a multiverse, where different regions of space exhibit varying physical laws. Each of these ideas represents a dramatic shift in how we view reality. demonstrating that the universe may be far more complex than we ever imagined. Alongside theoretical advances, technological breakthroughs have played a crucial role in pushing the boundaries of our knowledge. The launch of space telescopes such as Hubble, Chandra, Spitzer, and more recently James Webb has allowed us to observe cosmic phenomena in unprecedented detail. The James Webb Space Telescope, JWST, launched in 2021, has already provided revolutionary insights into the early universe by detecting galaxies that formed just a few 100 million years after the Big Bang. This capability allows astronomers to directly study the first stars and galaxies, shedding light on how structure emerged from the primordial chaos of the universe's infancy. But what is even more surprising is that JWST's findings have challenged existing models of galaxy formation. It has detected massive, mature galaxies that should not have had enough time to develop, according to standard cosmological predictions. This unexpected result has forced scientists to reconsider fundamental assumptions about the early universe and how quickly structures emerged. Another key area where technology has driven discovery is in the study of exoplanets' worlds orbiting other stars. The Kepler Space Telescope and its successor, TESS, have confirmed the existence of thousands of exoplanets, many of which reside in their star's habitable zone, where conditions might support liquid water and, potentially, life. More recently, JWST has begun analyzing exoplanet atmospheres, detecting the presence of molecules like carbon dioxide and water vapor, which could be crucial indicators of habitability. This marks a turning point in the search for extraterrestrial life, as we are now able to directly study the chemical composition of distant worlds. Could one of these planets harbor alien life? If so, what would that mean for humanity's understanding of its place in the cosmos? The discovery of even the simplest microbial life beyond Earth would be one of the most significant turning points in history, confirming that life is not unique to our planet and raising new questions about the frequency and evolution of intelligence across the galaxy. The study of black holes has also undergone a dramatic transformation in recent years. Once considered purely theoretical objects predicted by Einstein's general relativity, black holes have now been directly imaged, most notably with the Event Horizon Telescope, EHT. In 2019, the world was captivated by the first ever image of a black hole's Event Horizon, a glowing ring of light surrounding a region of complete darkness. This achievement provided direct confirmation of the existence of supermassive black holes at the centers of galaxies, reinforcing decades of theoretical predictions. More recently, the detection of gravitational waves, ripples in space-time caused by colliding black holes, has opened an entirely new way of observing the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterparts have recorded multiple gravitational wave events, providing insights into the mergers of black holes and neutron stars. This ability to listen to cosmic events rather than just see them represents a revolutionary shift in astronomy, allowing us to probe phenomena that were previously undetectable. Another significant turning point in cosmology is the growing realization that the Hubble constant, which describes the rate of the universe's expansion, may not be a fixed value after all. Different methods of measuring this constant yield conflicting results, a problem known as the Hubble tension. This discrepancy suggests that something fundamental may be missing from our current understanding of cosmic expansion. Could it be that dark energy behaves differently over time? Or that new physics, beyond the standard model, is at play? Some researchers speculate that the tension may hint at an unknown force influencing the universe, perhaps tied to extra dimensions or exotic particles that have yet to be discovered. These discoveries highlight a broader truth. The more we learn about the universe, the more questions arise. Rather than simplifying our understanding, each breakthrough seems to reveal deeper layers of complexity. This is the hallmark of a true turning point tone, where old assumptions must be reconsidered, where new models must be developed, and where the boundaries of knowledge are once again pushed outward. The 21st century is witnessing a revolution in physics and cosmology, one that will likely redefine our place in the cosmos in ways we cannot yet predict. As we move forward, what lies ahead? The next generation of telescopes promises even greater revelations. The upcoming Nancy Grace Roman Space Telescope will probe dark energy with greater precision, while the Square Kilometer Array (SKA) radio telescope will allow us to study the structure of the universe on an unprecedented scale. Future missions to Jupiter's moon Europa and Saturn's Enceladus may finally provide evidence of extraterrestrial life beneath their icy crusts, while advancements in quantum computing and artificial intelligence could help us unlock the deepest mysteries of physics. Perhaps the most exciting possibility is that we are on the brink of discovering a new fundamental force of nature, one that could finally unify quantum mechanics and general relativity. If such a force exists, it would be the most profound scientific turning point since Einstein's work over a century ago. It could explain dark matter, dark energy, and the unification of forces that physicists have sought for generations. But even if such a breakthrough eludes us, one thing is clear: the universe is not done surprising us. We stand at the edge of a new era, armed with technology that allows us to probe deeper into space than ever before. The discoveries of recent years have reshaped our understanding of the universe, forcing us to question our models and redefine the nature of cosmic expansion. The turning point is happening now, and its significance will ripple through generations, changing not just the way we see the cosmos, but the way we see ourselves. For centuries, our approach to understanding the universe has been shaped by a framework that assumes reality is something we can observe, measure, and define within a set of physical laws. But what if we are looking at the problem the wrong way? What if our perception of space, time, and matter is fundamentally flawed? In recent years, a growing number of scientists have begun to question whether our understanding of the cosmos needs a radical shift, a new way of thinking that moves beyond traditional theories and into realms where reality itself may not be as it seems. Concepts like the holographic principle, emergent space-time, and quantum gravity suggest that the universe is not what we once thought it was. These perspectives challenge conventional cosmology and force us to reconsider our most basic assumptions about the nature of existence. One of the most mind-bending ideas to emerge in theoretical physics is the holographic principle, the idea that the entire universe might be a projection of information encoded on a distant boundary. Originally proposed in the context of black hole physics, this theory suggests that just as a hologram on a two-dimensional surface can create the illusion of a three-dimensional object, our perception of a three-dimensional universe may actually be an emergent phenomenon of fundamental information stored on a distant cosmic boundary. This concept arose from studies of black hole entropy, where physicists like Jacob Bekenstein and Stephen Hawking found that the amount of information inside a black hole is proportional to its surface area, not its volume. This led to the realization that perhaps the universe itself functions similarly. What we experience as reality might be a projected image from a deeper, lower dimensional structure. If this is true, then space and time as we know them may not be fundamental aspects of reality, but emergent properties arising from more fundamental quantum information. This idea aligns with research in quantum gravity, where physicists attempt to reconcile the principles of quantum mechanics with general relativity. The problem with our current models is that Einstein's relativity describes space-time as a smooth, continuous fabric, while quantum mechanics suggests that at the smallest scales, everything is governed by uncertainty, probability, and wave functions. These two descriptions of reality are fundamentally incompatible, leading to paradoxes when applied to extreme conditions, such as the singularities inside black holes or the conditions of the early universe. The holographic principle provides one possible resolution to this conflict by suggesting that space-time itself is not fundamental, but rather emerges from deeper quantum structures. If this idea is correct, then our current way of thinking about cosmic expansion, the Big Bang, and the fabric of reality itself may need to be completely reimagined. Instead of asking what the edge of the universe is, we should perhaps be asking what space itself actually is. Is it a real, tangible thing? Or is it merely an illusion created by deeper forces of quantum information? This shift in perspective also forces us to reconsider the role of quantum mechanics in shaping cosmic structure. Traditionally, cosmology has treated the universe as something governed by large-scale forces, gravity, dark matter, and dark energy shaping the expansion of galaxies. But quantum physics tells us that even on these vast cosmic scales, uncertainty, entanglement, and wave-like behavior may play a fundamental role. One particularly fascinating idea is that the universe is entangled with itself, meaning that distant regions of space may be linked in ways we do not yet understand. If quantum entanglement plays a role in large-scale cosmic structure, then our attempts to define a single edge of the universe may be inherently flawed. What we perceive as separate, distinct regions of space could be deeply connected through quantum links that transcend our traditional understanding of causality. Another radical idea is that time itself might not be fundamental. Some physicists have proposed that what we perceive as time is merely a construct, an emergent property that arises from the interaction of quantum states. If this is the case, then the notion of a beginning of the universe becomes problematic. Was there truly a first moment, or is time something that emerges only at certain scales? If time is not fundamental, then the question of whether the universe is infinite or finite becomes meaningless. What we call the edge of the universe may simply be a limitation of our perspective rather than an actual boundary. Changing our viewpoint on these fundamental issues reshapes scientific discussions in profound ways. Traditional cosmology has operated under the assumption that we can model the universe using deterministic laws that allow us to make clear predictions. However, the growing realization that space, time, and even reality itself may be emergent phenomena means that we must develop entirely new ways of thinking. Instead of trying to map out the universe as if it were a static object, we must start considering it as a fluid, ever-evolving system whose properties depend on observation, information, and fundamental quantum behavior. This shift in thinking is already beginning to take shape. Research into quantum gravity, particularly efforts to develop a theory of everything, is moving toward models where space-time emerges from deeper networks of quantum interactions. The idea of a quantum universe, where space is not a fixed backdrop but a dynamic, fluctuating structure, is gaining traction. Some researchers believe that these quantum effects could explain dark energy and dark matter not as new particles or forces, but as emergent properties of a deeper quantum reality. If this is true, then our search for these missing components of the universe may need to shift away from traditional particle physics and toward entirely new conceptual frameworks. Additionally, the study of black holes has provided hints that our understanding of the universe may be incomplete. The black hole information paradox, which asks what happens to information that falls into a black hole, suggests that the universe operates under rules that are still unknown to us. Recent work in string theory and quantum gravity proposes that information is never truly lost, but may be stored in holographic patterns at the event horizon, or even in other dimensions. This could mean that the same principles apply to the universe as a whole if black holes encode information in a holographic way. Perhaps the entire universe functions similarly. One of the most exciting aspects of this paradigm shift is that it opens the door to entirely new scientific approaches. If space and time are emergent, then our traditional tools such as measuring distances, mapping cosmic expansion, and calculating gravitational effects may only be approximate descriptions of a deeper reality. Future discoveries may require us to rethink not only how we study the universe, but what we consider fundamental in the first place. Some physicists speculate that quantum computers, with their ability to process vast amounts of entangled information, could provide insights into these deeper structures, revealing patterns that are invisible through classical physics. The ultimate question remains, are we ready to let go of our assumptions? Throughout history, major scientific breakthroughs have required a willingness to abandon long-held beliefs. The transition from a geocentric to a heliocentric model, the shift from Newtonian physics to relativity, and the emergence of quantum mechanics all required scientists to embrace new perspectives that initially seemed counterintuitive. We may now be on the verge of another such transformation, one that forces us to reconsider what space, time, and the universe actually are. Perhaps we have been asking the wrong questions all along. Instead of searching for the edge of the universe, we should be asking whether the universe, as we understand it, is even the correct framework for reality. Instead of trying to fit dark matter and dark energy into our existing models, we should consider whether these phenomena are telling us that our entire approach to physics needs revision. Instead of treating space as an empty void where matter moves, we should be investigating whether space itself is a quantum construct, a vast network of entangled information. In the end, the search for truth is not just about finding answers, it is about challenging perspectives. The greatest breakthroughs in science come not from simply refining existing models, but from daring to think in ways that were previously unimaginable. We may be standing on the precipice of such a revolution right now, one that redefines the very nature of the universe, not as a physical structure with an edge, but as something far more intricate, woven from the deepest layers of reality itself. Throughout history, science has been a process of challenging assumptions, refining models, and uncovering hidden truths. Each discovery has brought us closer to understanding the vast cosmos. Yet just when we think we have grasped its nature, new findings emerge that shatter our preconceived notions. We have mapped the expansion of the universe, detected the ghostly presence of dark matter, and confirmed the existence of black holes. Yet we still face mysteries so profound that they force us to reconsider everything we thought we knew. What if, in our quest for cosmic truth, we have overlooked something fundamental? What if the universe is not what it appears to be? The last few decades have seen an unexpected twist in our understanding of reality, where the most groundbreaking discoveries are not merely refining our models, but suggesting that our very perception of the universe may be an illusion. One of the most unsettling realizations in modern physics is that our universe may not be the only one. For years, the concept of a single self-contained universe governed by fixed physical laws was the foundation of cosmology. But theories such as eternal inflation, quantum mechanics, and string theory have introduced the idea that our cosmos may be just one of an infinite number of universe or multiverse. The evidence for this idea is indirect but compelling. According to inflation theory, in the moments after the Big Bang, space-time expanded at an exponentially fast rate. This process, known as cosmic inflation, is believed to continue in different regions of space, creating bubble universes that are completely separate from our own. If true, this means that there are countless other realities, each with different physical laws, different particles, and possibly even different versions of ourselves. The implications of the multiverse are staggering. If there are infinite universes, then every possible outcome of every event has happened somewhere. In some realities, stars never formed. In others, entirely different forces govern physics. If consciousness exists in one universe, could it exist in others? Are there versions of us living parallel lives in other realms? The idea that there are infinite variations of reality calls into question everything we think about fate, individuality, and existence itself. It suggests that our universe is not special, but merely one possibility among an uncountable number of possibilities. It also raises an even more unsettling question. If we live in one of many universes, why are we here? Are we merely in a random cosmic bubble? Or is there some deeper reason that we find ourselves in this particular reality? But the twist does not end there. Some physicists argue that the multiverse itself is not real, but a flawed concept arising from an even more disturbing truth. The universe might not be fundamental at all. Over the last 2 decades, scientists have explored the simulation hypothesis, the idea that our universe could be a vast computational construct. Proposed by philosopher Nick Bostrom, this theory suggests that an advanced civilization with immense computational power could create simulated realities indistinguishable from the real thing. If such a civilization ever came into existence, it is likely that they would run countless simulations of past civilizations, meaning that the probability that we ourselves are in a simulation is higher than the probability that we are in a base reality. At first glance, this idea seems like science fiction, but several pieces of evidence suggest it might be worth taking seriously. Quantum mechanics, for example, describes reality as a set of probabilistic outcomes rather than fixed, deterministic events. This is remarkably similar to the way computers process information, where variables do not take on definite values until they are observed, a concept eerily reminiscent of wave function collapse in quantum physics. Additionally, some physicists have discovered strange mathematical patterns in the fundamental laws of nature, such as error-correcting codes similar to those used in computer programming. If the universe is a simulation, it would explain some of the biggest mysteries in physics, such as why the fundamental constants of nature seem fine-tuned for life. or why quantum mechanics allows for bizarre behaviors like entanglement, where two particles instantly affect each other across vast distances. If true, this realization would represent the greatest twist in human understanding of reality. The idea that we are living in a designed, artificial construct would have profound implications for everything from physics to philosophy. Are we merely characters in an advanced program running on an unknown substrate? If so, what is the nature of the beings running the simulation? Are they scientists running an experiment? Are they ancestors recreating their history? Could they themselves be simulated? Even if we never prove the simulation hypothesis, its implications force us to question the fundamental nature of existence. If the universe is designed, then who or what is the designer? If it is artificial, can it be manipulated or altered? Could there be a way to break out of the simulation, or at least understand its true nature? But perhaps the most shocking twist is not that the universe is a simulation or part of a multiverse, but that our entire concept of reality is an illusion created by our own minds. Some of the latest research in quantum mechanics and consciousness suggests that the observer plays a fundamental role in shaping reality. Experiments like the double-slit experiment show that particles behave differently when observed, leading to interpretations where consciousness itself affects the physical world. Some physicists suggest that reality does not exist in a definite state until it is observed, meaning that the universe, as we know it, is being constructed moment by moment by the act of perception. This idea aligns with certain interpretations of quantum mechanics, such as relational quantum mechanics, which suggests that objects do not have inherent properties until they interact with an observer. If this is true, then our understanding of the universe as an independent, objective reality is fundamentally flawed. Instead, what we perceive as the cosmos may be a set of relationships, a network of interactions, where nothing has a definite state until it is experienced. This means that the very fabric of reality is not fixed, but shaped by our consciousness, leading to a radical new perspective. Perhaps the most important element in the universe is not space, time, or matter, but awareness itself. If reality is observer-dependent, then this changes everything about how we view our place in the cosmos. The universe is not a vast, empty, meaningless expanse, but a participatory system where consciousness plays a fundamental role. This means that our thoughts, perceptions, and experiences may be more powerful than we realize. Could this be the reason why quantum mechanics defies classical expectations? Could this explain why reality seems so finely tuned for life? If consciousness is a fundamental part of existence, then perhaps our role in the universe is not to merely observe, but to create. The unexpected twist in our understanding of the cosmos is that we may never find an absolute answer, because the nature of reality itself is not absolute. Whether through the multiverse, the simulation hypothesis, or the role of consciousness in shaping existence, the very idea of a final truth may be a flawed assumption. Instead of searching for a single explanation, we may need to embrace the idea that reality is fluid, dynamic, and shaped by the perspectives we bring to it. The final realization is this: perhaps we are not simply passive observers of the universe, we are active participants in its unfolding. Our search for meaning, our desire to understand, and our drive to explore may not just be human instincts, they may be woven into the very fabric of existence itself. Whether we live in a multiverse, a simulation, or a quantum network of interactions, one thing remains certain: the quest for truth is what defines us. The greatest twist of all may not be what we find at the end of our search, but the realization that the search itself is what makes us human. Despite the incredible advancements in our understanding of the universe, we are still faced with profound and complex challenges that push the limits of human knowledge. The cosmos continues to present questions that we are not yet equipped to answer, and as we push deeper into space, the boundaries of our current technology and scientific methods become clear. While we have made astonishing progress in understanding cosmic expansion, black holes, dark matter, and dark energy, many hurdles remain before we can claim a comprehensive understanding of the universe. Addressing these challenges will require revolutionary advancements in observational technology, next-generation space missions, and fundamentally new ways of thinking about the nature of reality. The limitations of current observational technology. One of the greatest obstacles in modern cosmology is the inherent limits of observation. While telescopes such as the Hubble Space Telescope, HST, and James Webb Space Telescope, JWST, have pushed the boundaries of what we can see, they are still confined by the laws of physics. The observable universe is limited by the speed of light. We can only see as far as light has had time to travel since the beginning of the universe, meaning vast regions of space beyond that remain completely inaccessible to us. No matter how advanced our telescopes become, we will always be constrained by this cosmic horizon, leaving us forever unable to directly observe what lies beyond. Moreover, even within the observable universe, there are countless objects and phenomena that remain hidden from view. Dark matter and dark energy, which together make up approximately 95% of the universe, have yet to be directly detected. While we can infer their existence through gravitational effects and cosmic expansion, we have no way of seeing them. Current instruments simply do not have the sensitivity to identify dark matter particles, and dark energy remains an even deeper mystery, known only through its repulsive influence on cosmic acceleration. Without new breakthroughs in detection technology, we will remain in the dark, quite literal about the fundamental forces shaping our universe. Another major limitation is that we are only able to study the universe from one vantage point, Earth, and its immediate surroundings. While space telescopes have allowed us to observe distant galaxies and cosmic events, we are still bound by our location within the Milky Way. This limits our ability to test theories about the large-scale structure of the universe and makes it difficult to determine whether certain observations are truly universal laws or simply local phenomena. The possibility that fundamental physical laws vary in different parts of the cosmos is an unsettling thought, but without the ability to test physics beyond our observable reach, we may never know for sure. The need for next-generation space missions. To overcome these limitations, scientists are designing next-generation space missions that will push the boundaries of what we can observe and measure. Some of the most ambitious projects currently in development include the Nancy Grace Roman Space Telescope, 2027 launch. Often called Hubble's successor, this telescope will conduct high-resolution surveys of dark matter and dark energy, helping to refine our understanding of cosmic expansion. The Square Kilometer Array, SKA, 2020S-2030S, a revolutionary radio telescope network designed to probe the early universe, mapping hydrogen distribution and detecting signals from the first stars and galaxies. The Einstein Telescope, ET, 2035S expected, a next-generation gravitational wave observatory that will detect signals from merging black holes and neutron stars with unprecedented sensitivity, offering insights into space-time itself. Interferometric telescopes on the Moon. NASA and other space agencies are exploring the possibility of placing radio telescopes on the far side of the Moon, where the absence of Earth-based interference will allow for clearer detections of faint cosmic signals. The Next-Generation Very Large Telescope, ELT 2030S, the world's most powerful ground-based telescope, capable of studying exoplanet atmospheres in search of biosignatures. LUVOIR, Large UV, Optical, IR Surveyor, 2040S, a proposed successor to JWST, designed to explore the atmospheres of Earth-like exoplanets and study the first galaxies formed after the Big Bang. These missions represent a leap forward in our ability to explore the universe, but they also come with significant challenges. Funding, technological development, and logistical hurdles remain barriers to their completion. The sheer cost of deep space missions, often in the range of billions of dollars, means that many projects take decades to come to fruition. Political and economic factors can delay or cancel missions entirely, limiting the progress of scientific exploration. The challenge of understanding dark matter and dark energy. One of the greatest unresolved questions in cosmology is the true nature of dark matter and dark energy. While we have inferred their presence from gravitational effects and cosmic expansion, we still do not know what they are. Current hypotheses suggest that dark matter could be composed of weakly interacting massive particles, WIMPs, axions, or even primordial black holes. But no conclusive evidence has been found for any of these explanations. Experimental searches, such as deep underground particle detectors and the Large Hadron Collider, LHC, have yet to find definitive proof of dark matter's nature. Dark energy is an even greater enigma. Unlike dark matter, which interacts with gravity, dark energy is responsible for the accelerating expansion of the universe, and we have no solid theoretical framework for understanding what causes it. Some physicists speculate that dark energy could be vacuum energy, a property of empty space itself. Others suggest it might be a sign of a deeper, unknown force that governs the cosmos. Future telescopes and experiments will focus heavily on mapping the distribution of dark matter and tracking the effects of dark energy, but solving these mysteries will likely require entirely new physics beyond the standard model. How scientists plan to tackle unanswered questions. As we push forward in cosmology, physicists and astronomers are devising new ways to test theories and refine models. Some of the most promising approaches include quantum gravity research. One of the biggest gaps in physics today is the lack of a unified theory that reconciles quantum mechanics, which governs the small-scale world, with general relativity, which explains gravity, and large-scale cosmic structure. Theories such as loop quantum gravity, string theory, and emergent space-time models aim to bridge this divide. Laboratory simulations of cosmic conditions. Some scientists are attempting to recreate early universe conditions in laboratory settings using high-energy particle collisions and plasma physics. Artificial intelligence in cosmology. Machine learning is being used to analyze vast amounts of astronomical data, identify patterns in cosmic expansion, and even search for signs of extraterrestrial life. Searching for extra dimensions. Some theories propose that our universe is embedded in a higher dimensional space, with extra dimensions beyond the familiar 3 of space and 1 of time. Experiments at the LHC and upcoming particle accelerators may provide hints about these extra dimensions. The philosophical challenge. Can we ever fully understand the universe? Beyond technological and observational challenges, there is a deeper question. Is the universe fundamentally comprehensible? Or are there limits to what humans can ever know? Some physicists argue that we may never be able to probe beyond the cosmic horizon, leaving us permanently unable to answer some of the biggest questions. Others suggest that new ways of thinking, perhaps incorporating ideas from quantum mechanics, information theory, or even consciousness studies may be needed to unlock the final secrets of reality. If the universe is a holographic projection, a multiverse, or even a simulation, what does that mean for the future of physics? Do we need a new conceptual framework entirely? If time, space, and reality itself are emergent properties rather than fundamental structures, then we may be asking the wrong questions about the nature of the cosmos. This shift in perspective will require scientific humility and openness to ideas that may seem radical today, but could define physics in the future. Conclusion. The road ahead. The next century of exploration promises to be one of unprecedented discovery. We are on the verge of breakthroughs that could reshape our understanding of everything from the structure of space-time to the existence of extraterrestrial civilizations. Yet, the road ahead is filled with challenge technological, observational, and philosophical. Whether we find answers or more questions, one thing is certain: the quest for knowledge will never end. Science is not just about solving mysteries, but about embracing the unknown, pushing forward despite uncertainty, and always daring to ask what lies beyond the horizon. Final confrontation: the boundaries of the universe and the limits of knowledge. As humanity's understanding of the universe has expanded, so too has the debate over its true nature. Are we closing in on a final theory that unifies physics and explains the cosmos in its entirety? Or are we forever destined to be limited by observational constraints and theoretical paradoxes? The confrontation between competing ideas has reached a fever pitch in modern physics, where cutting-edge theories challenge fundamental assumptions about space, time, and reality itself. At the heart of this struggle lies the question: will we ever find a true boundary to the universe, or is our search inherently flawed? From the nature of cosmic expansion to the quest for a theory of everything, this is the defining battle of modern cosmology. The latest competing theories and their strengths While classical physics once treated the universe as a singular, self-contained entity, the discoveries of the 20th and 21st centuries have revealed a far stranger and more complex reality. Several competing theories now vie for dominance, each offering unique insights while presenting new challenges. The infinite universe hypothesis, one of the most accepted ideas in cosmology, is that the universe has no physical boundary, extends infinitely in all directions. This theory is based on observations of large-scale cosmic structure, which show no evidence of an edge or enclosed space. The cosmic microwave background, CMB, appears statistically uniform, suggesting that space continues beyond what we can observe. Strengths: aligns with general relativity, matches large-scale observations, and avoids the paradoxes associated with a cosmic edge. Weaknesses: if the universe is infinite, how did it originate? If it has always existed, this contradicts models suggesting a Big Bang-like singularity. Additionally, if infinity is real, then all possible arrangements of matter, including alternate versions of Earth and ourselves, must exist somewhere in the cosmos, a conclusion that defies intuition. The finite but unbounded universe. Some models propose that the universe is finite in size but has no edge, much like the surface of a sphere, which is limited in area but has no physical boundary. In this scenario, traveling in one direction long enough might bring an observer back to their starting point. Strengths: solves the problem of an arbitrary cosmic edge and aligns with Einstein's relativity, which allows for curved space-time. Weaknesses: no observational evidence has yet confirmed a closed-loop structure, and it is unclear what conditions could allow such a topology while still matching cosmic expansion data. The multiverse theory. Some physicists argue that our universe is merely one of many universes, each with its own physical laws. This idea arises from cosmic inflation, which suggests that new regions of spacetime continue to form outside our observable universe, potentially leading to an infinite number of independent bubble universes. Strengths: explains why our universe's physical constants appear fine-tuned for life. If many universes exist with different properties, we happen to be in one that permits our existence. Also supported by certain interpretations of quantum mechanics, such as the many worlds hypothesis. Weaknesses: no direct observational evidence, and critics argue that a theory that predicts everything predicts nothing. It is impossible to falsify, making it scientifically problematic. The holographic universe. One of the most radical proposals in physics suggests that our entire three-dimensional universe is actually a projection of information encoded on a distant two-dimensional boundary. This is known as the holographic principle, originally proposed in black hole physics. Strengths: supported by string theory and quantum gravity models, explains the paradox of black hole information and may provide a solution to the unification of gravity and quantum mechanics. Weaknesses: a deeply counterintuitive idea with limited experimental support, requiring a drastic shift in our understanding of what space and matter actually are. The ongoing debate: will we ever find a true boundary? The question of whether the universe has an edge remains one of the most hotly contested debates in cosmology. If there is a boundary, what lies beyond? If there is no boundary, how do we reconcile that with the idea of a finite past and a beginning at the Big Bang? The problem is further complicated by the horizon limit. We can only observe regions of space where light has had time to reach us, meaning that the true structure of the universe may forever remain beyond our reach. Some physicists argue that the universe's ultimate structure may be unknowable, not because of technological limitations, but because our models of reality may be fundamentally incomplete. If space-time is emergent rather than fundamental, then asking where the edge is might be the wrong question. Instead, we may need a new framework that describes the universe not as a fixed structure, but as a dynamic, evolving information network. Unifying physics, bridging relativity and quantum mechanics. One of the biggest unresolved challenges in physics is the need to unify general relativity, which describes gravity, and large-scale cosmic structure, with quantum mechanics, which governs particles and fundamental forces. These two pillars of physics work exceptionally well in their respective domains, but contradict each other in extreme conditions, such as inside black holes or during the first moments of the Big Bang. several approaches have emerged to tackle this problem. String theory proposes that all particles and forces arise from tiny vibrating strings of energy existing in extra dimensions beyond our perception. It provides a mathematical framework for quantum gravity, but lacks direct experimental evidence. Loop quantum gravity suggests that space-time itself is quantized, made up of tiny, discrete units rather than a continuous fabric. This theory removes singularities from black holes and the Big Bang, but is still in early development. Causal dynamical triangulations, CDT, is an attempt to describe space-time as a self-organizing system of interacting units, evolving dynamically rather than being a fixed background. Each of these theories represents an attempt to resolve the inconsistencies between quantum mechanics and relativity, but none have yet succeeded in producing testable predictions that can confirm them. Until a successful quantum gravity theory is developed, our understanding of the universe remains incomplete. The future of cosmology. As we stand on the frontier of discovery, the future of cosmology is likely to be shaped by several key developments. Next-generation observatories, new telescopes such as the James Webb Space Telescope, the Vera-C, Rubin Observatory, and the European Extremely Large Telescope, ELT, will provide unprecedented data on the structure of the early universe and dark matter. Gravitational wave astronomy. With new detectors, we will be able to probe deeper into the fabric of space-time, testing relativity in extreme conditions, dark matter, and dark energy research. Upcoming experiments, such as the Large Synoptic Survey Telescope, LSST, and Euclid mission, will help refine our understanding of the unseen forces governing the universe. Quantum computing and AI in physics. Advances in computational power will allow simulations of quantum gravity models, potentially unlocking new insights into the fundamental structure of space-time. The ultimate question: what if there is no final answer? One of the most unsettling possibilities is that we may never reach a final, complete theory of the universe. If reality itself is emergent, holographic, or shaped by deeper structures beyond our comprehension, then the notion of a single, final truth may be a human construct rather than a physical reality. If so, then the quest for understanding is not about reaching an endpoint, but about continuously refining our perspectives, adapting to new discoveries, and embracing the complexity of the cosmos. Perhaps the final confrontation is not between competing scientific theories, but between our desire for certainty and the reality of an ever-changing universe. Regardless of what the future holds, one thing remains clear: the search for truth will never end. The greatest revelations may still lie ahead, waiting to be uncovered by those who dare to challenge the limits of human knowledge. Moral takeaway: the lessons of the cosmos. The universe is more than just an expanse of stars, galaxies, and cosmic voids. It is a vast arena where humanity's deepest questions collide with the limits of our understanding. As we venture further into the unknown, our discoveries force us to confront not only the nature of reality, but also the nature of ourselves. What does it mean to search for answers in a universe that may never fully reveal them? Is knowledge itself the ultimate goal, or does the mystery hold an intrinsic value of its own? The journey of cosmic exploration teaches us profound lessons about curiosity, humility, and the delicate balance between what we know and what we may never understand. The deeper meaning of exploring the unknown. At its core, the pursuit of understanding the universe is more than a scientific endeavor. It is a deeply human experience. From the earliest civilizations mapping the stars to modern-day physicists probing the mysteries of quantum gravity, our search for cosmic truths reflects an innate desire to find meaning in the vastness of existence. Why do we look to the sky? Because it represents everything beyond ourselves: the infinite, the ungraspable, the unknowable. This urge to explore is not driven solely by necessity or survival. It is embedded in our very nature. Unlike other species, humans seek not only to understand their environment, but to ask why it exists in the first place. The universe, in all its incomprehensible scale and mystery, compels us to reflect on the fragility and significance of our existence. If we are small, does that mean we are insignificant? If we are temporary, does that mean our experiences are meaningless? Or does the act of searching itself give meaning to everything we do? The philosopher Carl Sagan once remarked that we are a way for the cosmos to know itself. This perspective suggests that the universe is not merely an external entity we observe, but something we are an intrinsic part of. Every element in our bodies was forged in the hearts of ancient stars, scattered across space and time before coalescing into life on Earth. This realization connects us to something far greater than ourselves. We are not apart from the universe. We are of it, shaped by its forces, driven by its mysteries, and compelled to seek its truths. How curiosity drives scientific progress. Science is, at its heart, the pursuit of the unknown. Every major discovery in human history has been fueled by curiosity, by the willingness to question, challenge, and expand our understanding of what is possible. The most groundbreaking scientific advancements, from heliocentrism to relativity, from quantum mechanics to cosmic expansion, have all emerged from asking the right questions, not from accepting comfortable assumptions. If history has taught us anything, it is that certainty is an illusion. Every time humanity has believed it understood the structure of the universe, new evidence has forced us to rethink our models. The Earth was once believed to be the center of existence, only for Copernicus and Galileo to reveal its place in an unfathomably vast cosmos. Newtonian mechanics seemed to describe the universe perfectly until Einstein's relativity showed us that space and time themselves are not absolute. Even today, our most advanced theories of quantum mechanics and relativity remain incomplete, unable to reconcile with one another. This constant evolution of knowledge is not a failure, it is progress. It is a testament to the power of curiosity, to the recognition that not knowing is not a weakness, but an invitation to learn. Without this mindset, scientific progress would stagnate, and our understanding of the universe would be frozen in time. The exploration of the cosmos also serves as a reminder that true knowledge is never static. Every answer leads to new questions. Every discovery opens a new frontier, and every attempt to define reality brings us closer to realizing how much we have yet to uncover. The most successful scientists are not those who claim to have all the answers, but those who remain open to the ever-expanding mystery. The balance between knowledge and mystery. As much as we strive for knowledge, there is also value in the unknown. The mystery of the cosmos is not something to be feared, it is something to be embraced. If there were no unanswered questions, if we had already mapped every inch of the universe and understood every law governing its existence, then what would be left to inspire us? What would be left to wonder about? The beauty of science is not just in what we have discovered, but in what remains undiscovered. The thrill of exploration lies in the possibility of the unknown, in the excitement of standing on the edge of understanding, knowing that there is always more to see, more to learn, more to question. There is also a profound philosophical and spiritual aspect to this balance. Many of the greatest thinkers and history scientists, poets, theologians, and philosophers have all grappled with the idea that mystery is essential to meaning. The fact that we do not know the full nature of the universe forces us to stay humble, to acknowledge that our perspective is limited, and to remain open to the infinite possibilities of what may lie beyond. This is why the search for extraterrestrial life, for example, is so compelling, not just because we want to find aliens, but because the question itself expands our understanding of life, consciousness, and our place in the cosmos. The search matters because it forces us to redefine what we think is possible, to challenge the assumptions that life exists only in forms we recognize, and to consider that the universe may be far stranger than we ever imagined. Lessons humanity can learn from cosmic exploration. The lessons we learn from studying the universe extend far beyond science. The cosmos teaches us not only about space and time, but about our own nature as a species. There are moral, ethical, and existential insights to be gained from our exploration of the stars. Humility in the face of the vastness. The sheer scale of the universe reminds us that we are small, but that does not make us insignificant. It teaches us to respect the unknown, to recognize that our understanding is always evolving, and to appreciate the privilege of existing in such a vast, beautiful, and mysterious cosmos. Unity as a species. The universe does not recognize human divisions, borders, ideologies, and conflicts are irrelevant on a cosmic scale. When astronauts look back at Earth from space, they see a single, fragile world, not divided nations. Cosmic exploration encourages cooperation, as no single country or individual can fully uncover the secrets of the universe alone. The responsibility of knowledge. As we continue to push the boundaries of science, we must also consider the ethical implications of our discoveries. Advances in technology, space colonization, and artificial intelligence must be pursued with caution and wisdom, ensuring that knowledge is used to uplift humanity rather than destroy it. The power of curiosity and imagination. Every breakthrough in science, every artistic masterpiece, every leap in human thought has come from the same source: the ability to imagine beyond what we know. The cosmos teaches us that possibilities are endless, that reality is always deeper than it seems, and that our greatest tool is not just intelligence, but imagination. The importance of leaving a legacy. Humanity is young. If we do not destroy ourselves, we may one day become a multi-planetary species, ensuring that life, perhaps consciousness, itself continues to exist long after the Earth is gone. We have the ability to shape the future, to ensure that our presence in the cosmos is not just a brief flicker, but a lasting beacon of intelligence and exploration. Conclusion: the eternal journey. In the end, the greatest lesson from cosmic exploration is this: the journey never ends. There will always be new frontiers to explore, new questions to ask, and new mysteries to ponder. The pursuit of knowledge is not about reaching a final answer. It is about continuing to seek, to wonder, and to grow. As long as there are stars in the sky, as long as there are minds that ask why, the story of the universe and our place in it will continue to unfold. The final moral takeaway is not that we will ever fully understand the cosmos, but that the act of exploring, of questioning, of seeking to understand, is what truly defines us. The universe does not owe us answers, but it has given us something far more valuable: the desire to ask the questions.